A battery just came out of a factory in China that should not exist. That is not an exaggeration. For 30 years, battery scientists agreed on one thing. This exact battery could never work at a price anyone could actually afford. But it is real. It is being built right now by the millions, and it is about to show up in real cars on real roads, not in some lab 10 years from now. Here's what makes it so strange. This battery has no lithium inside it, not 1 gram. If you know anything about batteries, that should sound impossible. Lithium is the reason your phone lasts all day. It is the reason electric cars can drive hundreds of miles on one charge. For 30 straight years, lithium was basically the only real choice on the table. Now, a company has built something that skips lithium completely and somehow beats it in some of the toughest tests engineers can run. This new battery can charge to 80% in about 15 minutes, which is roughly as long as it takes to grab a coffee and wait in line. It can be charged and drained more than 10,000 times before it starts losing real power. To put that number in plain terms, if you charge this battery every single day without skipping one, it would still be working fine 27 years later. Most electric car batteries on the road today start wearing down after 3,000 or 4,000 charges. Cold weather is where things get even stranger. Drop the temperature to 40 degrees below zero, cold enough to freeze exposed skin in minutes, and this battery still holds onto 90% of its power. A normal lithium battery sitting in that same freezing cold can lose almost half its power just from the temperature alone. Ask anyone who owns an electric car in a place like Canada or Norway how much that matters on a January morning when the car will not give them the range they expected. Then there is the price. This new battery costs a fraction of what it takes to build a lithium one. Not a small discount either, a massive one. That is because it is built from sodium, one of the most common elements on the entire planet. You have probably touched some of it today without even thinking about it. It is sitting in the salt shaker on your kitchen table right now. This is also not a single prototype, sitting inside a quiet lab somewhere waiting for funding. Factories are already producing these batteries by the millions of units month after month, at a scale most brand new battery designs never reach, until years after they first get announced to the public. And this is not staying inside cars either. The same kind of battery is already lined up to power delivery trucks, city buses, and the giant walls of batteries that store power for whole neighborhoods after the sun goes down. One breakthrough, sitting quietly in a factory in China, is about to touch a lot more of daily life than most people realize right now. So here's the real question hanging over all of this. If sodium is this cheap, this safe in a fire, and this good in the cold, why did it take the biggest battery company on Earth 30 years to build one that actually works? Why did nearly every scientist before this basically give up on the whole idea? And now that it is finally real, what does that mean for the phone in your pocket, the car in your driveway, and the power grid that keeps your lights on? To understand any of that, we need to go back and look at why lithium became so powerful in the first place. Because this new sodium battery only makes sense once you understand exactly what it is trying to replace, and why almost nobody on Earth thought that replacement was even possible. Before we get into that though, here is something worth knowing. Stories like this one, where a quiet breakthrough ends up reshaping something huge in the background of everyday life, are exactly what we dig into on this channel. Not years after the fact, once everyone already knows about it, but while it is still happening. If that sounds like your kind of thing, hit subscribe now, because the next few sections are going to walk you through exactly how a company solved a problem that stumped scientists for over 40 years, and you will actually understand how it works by the end, not just that it does. The king. Nobody questioned. Right now, there's a lithium battery close to you. Maybe it is in your pocket. Maybe it is charging on your desk. Maybe it is sitting in a car parked in your driveway. Lithium batteries are everywhere, and most people never think twice about them. You just expect your phone to last the whole day. You expect your car to get you home. The trust did not happen by accident. It took 30 years to build, one small improvement at a time. Before lithium batteries existed, most devices ran on something called nickel-cadmium batteries. They were heavy, they were bulky, and they could barely hold enough power to last very long before needing a recharge. Then, in 1991, a company called Sony released the very first lithium battery sold to regular people. This was not a small step forward. It was closer to swapping a bicycle engine for a rocket engine. The new lithium batteries could hold roughly 3 times more energy than the old ones in the exact same amount of space. Suddenly, small and powerful gadgets became possible in a way they never had been before. A camcorder battery from 1991 lasted about an hour of recording time. Within just 10 years, that same size and weight of battery could keep a phone running for days at a time. Not long after that, lithium batteries were pushing electric cars down highways for hundreds of miles on a single charge. Once that shift happened, the money followed fast. More than $1 trillion poured into lithium battery research and factories over the next 30 years. Car companies built entire vehicles around lithium power from the ground up. Governments built their clean energy plans around it. Lithium became the quiet assumption sitting underneath nearly everything that needed portable power. Nobody questioned it because nobody had a reason to. So why did lithium win so completely? The simple answer comes down to weight. Lithium is one of the lightest metals that exists anywhere on the periodic table. Picture two boxes that are the exact same size. One is packed full of ping pong balls. The other is packed full of golf balls. Because ping pong balls are lighter, you can fit a lot more of them into that same box if your goal is packing in as many as possible. Lithium works in a similar way inside a battery. Because its particles are so light, engineers can pack a huge number of them into a small space. More particles packed into that space means more energy, stored for the same overall weight. There's also a partner material that makes lithium batteries work as well as they do. It is called graphite, and its job is to store the lithium particles while the battery is charging up. Picture graphite as a stack of flat playing cards, lined up perfectly on top of each other with tiny even gaps between each card. When you plug in a lithium battery to charge, lithium particles slide neatly into those gaps and settle there. When you use the battery to power something, those same particles slide back out again. The size of those gaps matches the size of a lithium particle almost perfectly, which means this sliding motion can happen thousands and thousands of times without wearing the structure down. Lithium has one more advantage too, and it has nothing to do with weight. It pushes electricity through a circuit harder than most other materials can manage, kind of like the difference between a garden hose running on normal water pressure and one hooked up to a much stronger pump. That extra push means engineers do not need to build a huge, bulky battery just to get useful power out of it. A small lithium battery can do a job that would take a much bigger battery built from almost anything else. For 30 years, this partnership between lithium and graphite kept getting better. Engineers found ways to pack in more power, charge things faster, and make batteries last longer with every new generation of phones, laptops, and cars. It became such a steady and reliable formula that almost nobody in the industry stopped to ask whether something better might be sitting right next to it the entire time, just waiting to be noticed. Think about everything that only exists because lithium made it possible. The smartphone in your hand would not exist without it. Wireless earbuds that fit inside your ear and still last all day would not exist without it. Electric cars that can actually compete with gas cars on range would not exist without it. Every one of those inventions needed a battery light enough and powerful enough to disappear into the background of daily life. And for 30 years, lithium was the only material on Earth that could do that job well enough to matter. But here's the thing about a system that works this well for this long. The same properties that made lithium so powerful were also quietly creating problems underneath the surface. Problems that most people had no idea were sitting inside their pocket, their laptop bag, or their own driveway, until those problems became impossible to ignore. Cracks in the crown. In 2016, Samsung released a phone called the Galaxy Note 7. It was supposed to be one of the best phones the company had ever made. The reviews were glowing. People rushed out to buy it. And then, within just a few weeks, something terrifying started happening. The phones began catching fire, in pockets, on nightstands while people slept, on airplanes mid-flight. Airlines banned the device completely from being carried on board. Samsung pulled every single unit off shelves around the entire world. The final cost to the company was about $5 billion, and the Note 7 became one of the most famous product disasters in modern history. Here's the part almost nobody talks about, though. This was never really about Samsung making a badly built phone. Samsung did make some specific mistakes putting that particular battery together. That part is true. But the real danger underneath it all was not something Samsung invented from scratch. It was sitting quietly inside every single lithium battery ever made, in every phone, every laptop, and every electric car on the road, whether it was expensive or cheap. Here is why. Inside a lithium battery, there's a liquid that helps carry charged particles back and forth as the battery charges and drains. That liquid happens to be flammable. If the battery gets too hot, gets punctured, or gets overcharged, that liquid can catch fire. And once one small part of the battery catches fire, the heat spreads to the section right next to it, and then the next one after that, like a long row of dominoes falling one after another inside a sealed metal box. Engineers have a name for this chain reaction. They call it thermal runaway. Once it truly starts, there's almost no way left to stop it. This is not just an old story from 2016 either. In New York City, fires linked to lithium batteries have become a real and growing problem over the past few years, mostly coming from cheap, poorly made batteries used in electric bikes and scooters. Since 2022, the city has logged hundreds of these fires and dozens of deaths tied directly to lithium batteries. Fire officials pushed hard on public safety campaigns because of it, warning people never to charge these batteries overnight or leave them near an exit while they sleep. Deaths dropped sharply after those efforts finally kicked in, which is genuinely good news. But the underlying danger has never fully gone away. The same chemistry causing that risk is sitting inside every lithium battery on Earth, no matter how cheap or expensive the device around it happens to be. A battery inside a $500 phone and a battery inside a $50 scooter charger both carry the exact same flammable liquid at their core. Then there is the cold weather problem, which is a completely different kind of headache. When the temperature drops low enough, the particles inside a lithium battery stop moving smoothly through the liquid around them. Instead, tiny metal spikes start forming inside the battery, almost like frost slowly building up on the inside of a car window on a freezing morning. Except these spikes do not melt away. They grow a little more with every single charge. If a spike eventually grows large enough to touch the wrong part of the battery, it creates what is called a short circuit. That short circuit generates heat very quickly, and heat inside a lithium battery, as the Note 7 proved in the most expensive way imaginable, rarely ends well for anyone nearby. Even without that worst-case scenario ever happening, cold weather alone causes a real and measurable problem every single winter. At freezing temperatures, a lithium battery can lose somewhere between 20 and 40% of its usable power. Nothing inside the battery is actually broken in this case. It is simply too cold outside for the chemistry to work at full strength. For someone starting up their electric car on a freezing morning in a place like Minnesota or Alberta, that can mean losing 60 miles of range or more before they have even backed out of the driveway. Now here comes a part of the story that has nothing to do with chemistry at all and everything to do with geography. Just 3 places on Earth, Australia, Chile, and China, control roughly 90% of the world's mined lithium. China alone processes most of that raw material into battery-grade form and builds well over 8 out of every 10 batteries made anywhere on the planet. That means almost every electric car, laptop, and home battery system in the world depends on a supply chain running through a surprisingly small handful of places on a map. That kind of dependence gets dangerous fast whenever prices start moving, and lithium prices move a lot, sometimes in wild and unpredictable ways. Between 2020 and 2022, the price of raw lithium jumped by 8 times its starting value. Not 8% higher, 8 times more expensive in just 2 years. Then, in 2023, the price crashed by more than 70% in a single year, wiping out most of those earlier gains almost overnight. Try to imagine running a car factory or a battery plant while planning years ahead around a material that behaves less like a stable resource and more like a wild roller coaster ride. Nobody can predict the shape of in advance, one where the biggest drop always seems to come right after you have committed all your money to the climb. Now stack that price problem on top of the fact that almost the entire supply comes from just 3 countries. It is a bit like an entire city getting its drinking water from a single pipe. Most days, that pipe works fine and nobody thinks about it. But the moment something goes wrong with that one pipe, whether it is a price spike, a trade dispute, or a factory slowdown, the whole city feels it at once with no backup system ready to take over. For a car company planning to build 1 million vehicles a year, that kind of price swing can mean the difference between healthy profit and a huge loss. Based entirely on a material price nobody at the company has any real control over. None of these problems were exactly hidden from car makers and phone companies either. Engineers built cooling systems to keep batteries from overheating. They wrote software that slows down charging whenever a battery gets too hot or too cold. They added extra layers of protection around battery packs in cars so they could survive a crash without catching fire. All of that helped around the edges. None of it fixed the actual problem sitting at the center of the battery itself, because the core chemistry underneath all of it never changed. So here's where things stood, all stacked up at once. Lithium built the modern world we live in today. It also carried a real risk of catching fire, a real weakness in cold weather, and a supply chain controlled by a tiny number of countries who could shift prices however they liked. None of these problems were secret. Engineers had known about most of them for years and had written about them in plenty of reports. But when something is working well enough and the profits keep rolling in steadily, most industries simply do not go looking hard for a replacement. Why fix something everyone has already learned to live with? It usually takes a real shock to change that pattern. A fire that cost $5 billion, a price that jumps 8 times in 2 years flat, a supply chain that suddenly feels far too fragile to trust completely. That kind of shock is exactly what finally sent one company back to an old idea that had been sitting quietly on a shelf since the 1960s, mostly forgotten by everyone else in the industry. The comeback 50 years in the making. Long before lithium batteries existed, scientists were already experimenting with a completely different element for storing power. That element was sodium. It sits right next to lithium on the periodic table, and it behaves in a fairly similar way chemically. It is also everywhere you look, once you know to look for it. It is dissolved in seawater. It is packed inside rock formations on every single continent. It is sitting in the salt shaker on your kitchen table this very moment. In 1966, engineers at Ford built the very first high-powered rechargeable battery ever made using sodium instead of lithium. Sodium actually came first in this whole story, years before lithium even entered the picture. but there was a massive problem standing in the way. That early battery had to run at around 300 degrees just to function at all, hot enough to melt a bar of lead. It was a fascinating science experiment sitting in a lab. It was completely useless for anything a normal person could ever plug in and use at home. Then in the early 1970s, a scientist figured out how to build a lithium battery that could work at normal room temperature. That single discovery changed the direction of everything that followed. Suddenly, lithium had a massive advantage that sodium simply did not have. It worked at the same temperatures humans actually live and work in every day. From that point forward, almost all the money and research attention in the entire battery world flowed toward lithium instead. Sodium got quietly pushed aside and mostly forgotten for the next several decades. It was not just bad timing either. Sodium carried a real technical problem that nobody could figure out how to solve. Sodium particles are roughly 35% bigger than lithium particles, which sounds small until you remember how precise batteries need to be. Remember that neat stack of cards inside a lithium battery, with gaps sized perfectly for lithium particles to slide through smoothly? Sodium particles are simply too big to fit through those same gaps without causing damage. Every single time a sodium particle tried to force its way in, it pushed the stack apart a little bit more. After just a few hundred charges, the whole structure would fall apart and stop working. Lithium, meanwhile, was already lasting thousands of charges without any trouble at all. That gap in performance kept sodium locked out of serious consideration for more than 40 years, straight. Here is where the story finally starts to turn. Researchers eventually discovered a completely different kind of material that could actually work with sodium's larger size instead of fighting against it. It is called hard carbon. If graphite is a neat, perfectly stacked deck of playing cards, hard carbon is what that exact same deck looks like after someone throws it up into the air, lets every card scatter across the floor in a mess, and then somehow freezes the whole thing in place exactly as it landed. It looks chaotic, it looks uneven. And it turns out that messiness is precisely what sodium needed the entire time. Hard carbon gets made by heating up plant material, things like leftover waste from crops or even simple plant sugar, to extremely high temperatures with absolutely no oxygen anywhere nearby. Even the raw ingredients going into it are strangely ordinary. Some factories use leftover corn husks, others use coconut shells or scraps of wood that would normally just get thrown away or burned as waste. That leftover material gets turned into one of the most important parts of a brand new kind of battery. This process locks the carbon into a jumbled, uneven structure full of odd little gaps and pockets of all different sizes. Those uneven gaps turn out to be big enough and varied enough for sodium particles to slide comfortably in and out without wrecking the surrounding structure the way graphite always did. For the very first time in the entire history of this technology, sodium finally had a real home inside a battery that could survive years of daily use without falling apart. But there was still one more catch hiding in the details, and it is one most people never hear about. Hard carbon soaks up moisture from the air almost exactly like a kitchen sponge left out on the counter. Even a tiny trace amount of water trapped inside a finished battery can react badly with the chemicals around it, creating gas, building up pressure inside the sealed cell, and slowly wrecking the whole battery from the inside out over time. That kind of problem is manageable if you are working carefully inside a small lab. It becomes a genuine nightmare when you are trying to build millions of these batteries on a factory line and ship them safely around the entire world. This is exactly the problem that one company decided to spend years solving properly instead of walking away from it. KTL, the largest battery maker on the planet, began serious sodium battery research back in 2016 and poured in close to 10 billion yuan, somewhere around $1.4 billion, over roughly a decade of steady work. That kind of money and patience is rare in an industry where most companies want results within a couple of years, not 10. First, their engineers changed the surface chemistry of the hard carbon itself, swapping out the parts that soaked up water for parts that actively pushed water away instead, almost like waxing a car hood so rain slides right off instead of soaking in. Then they figured out how to control the exact size of those tiny internal gaps with almost unbelievable precision, working at a scale smaller than almost anything the human eye could ever picture clearly. Make the gaps too small, and sodium particles cannot slide in efficiently. Make them too big, and you waste space you could have used to store more power. Getting that balance exactly right over and over again across millions of battery cells rolling off a factory line took years that most companies were simply not willing to spend. Plenty of competitors looked at the same problem, ran a few tests, and quietly walked away. KTL kept going. The result of all that patient work is a battery CATL, now called Naxtra, and its numbers sound almost unbelievable for something built out of ordinary salt. Naxtra can store enough energy to push a car more than 300 miles on a single charge, putting it right in the same range as many everyday lithium batteries used in affordable electric cars today. It charges to 80% in about 15 minutes, roughly the time it takes to eat a quick breakfast. It survives more than 10,000 full charges before it starts wearing down in any meaningful way, which works out to roughly 3 times what most long-lasting lithium batteries can handle over their entire lifespan. At 40 degrees below zero, cold enough to stop a normal lithium car in its tracks, Naxtra still holds on to about 90% of its full power. And because sodium, along with the other materials used to build it, is so common and widely available, its price is not tied to the same wild swings that have hit lithium prices again and again over the years. There's one honest limit worth being upfront about here. Because sodium particles are bigger and heavier than lithium particles, there's a natural ceiling on how much power you can pack into a very small, very lightweight space. That limit matters enormously for something like an airplane, where every single extra pound of weight costs real fuel and real range. It matters a lot less for cars, buses, delivery trucks, and the massive battery systems built to store power for entire neighborhoods and cities. Those are exactly the areas where sodium is now stepping in and proving itself. KATL is not even stopping at building a single new type of battery either. They have already built a car battery pack split into 2 separate sections, one running entirely on sodium and one running entirely on lithium, with built-in software deciding in real time which section to draw power from. On a freezing morning where lithium usually struggles, the sodium half quietly takes over the load. On a long highway drive that demands maximum range, the lithium half steps up instead. Rather than picking one single winner and walking away from the other, the plan is to let each type of battery handle the exact job it happens to be naturally best at. Almost like 2 runners tag, teaming different legs of the same long race. This is already happening right now, not sitting years away as some distant future plan still stuck on a whiteboard. CATL has already passed strict new government safety tests in China, including crush tests, nail tests, and saw tests where engineers deliberately tried to destroy the battery on purpose, and it kept working without producing any smoke or flames at all. Their sodium batteries are heading into real vehicles from major car brands as you watch this. A Chinese automaker called Chang'an has already announced a car built around this exact battery, expected to hit the market by the middle of 2026. That would make it the very first mass-produced electric vehicle anywhere in the world powered entirely by sodium instead of lithium, something almost nobody would have predicted just a few short years ago. CATL is also rolling this technology into battery swap stations, the kind of setup where instead of waiting to charge your car, you simply pull in and swap your empty battery for a full one in a few minutes, similar to how you might swap a propane tank at a gas station. Hundreds of these stations are already running, with plans for thousands more over the next couple of years, and sodium batteries are a natural fit for that kind of heavy, repeated daily use. What happens next? Here is where this story grows into something much bigger than just one company or one clever battery, because sodium is not staying confined inside cars for very long. Huge battery systems built to store power for entire neighborhoods, factories, and power grids need batteries that can charge and drain over and over again, day after day, for years on end without complaining. Cost and reliability matter far more there than squeezing every last bit of power into the smallest possible space. That is exactly where sodium fits in best. Companies around the world are already testing and rolling out sodium battery systems specifically built for this kind of large-scale energy storage. The giant battery warehouses that quietly keep power flowing to homes even when the sun goes down or the wind stops blowing. There's another growing use case that most people never think about at all. The huge computer centers that run the internet and now power artificial intelligence need enormous amounts of backup power that can kick in instantly if the main electricity supply ever fails. That demand is only growing bigger every year. A battery that is cheap, safe from fire, and able to charge and drain constantly without wearing out fits that job almost perfectly. And sodium batteries are already being looked at as a serious option there too. The price story is moving fast too, and it is worth paying attention to. Right now, sodium batteries cost roughly the same as budget-friendly lithium batteries, sometimes a touch more, sometimes a touch less, depending on exactly who you ask and which factory you're comparing. But most industry experts expect that gap to shift hard in sodium's favor within just the next few years, as more factories get built and production scales up around the world. Some estimates suggest sodium battery prices could match or even beat cheap lithium batteries by the end of 2026, and keep dropping steadily after that as the whole supply chain matures. Not every company betting on sodium has gotten a happy ending, though, and that part of the story deserves to be told honestly. In the United States, a company called Natron Energy was once one of the biggest names working on sodium battery technology, with big plans and government support behind it. In September of 2025, they shut down completely, closing every factory they had and canceling a planned $1.4 billion battery plant that was supposed to create over 1,000 jobs. It is a sharp reminder that having promising technology is never enough on its own. You also need the money, the customers, and the sheer manufacturing scale to actually pull it off at a massive level. Right now, China is the one making that happen successfully, in much the same way it already dominates lithium battery production today. That last point matters more than it might seem at first glance. One of the biggest promises of sodium batteries was supposed to be breaking free from a supply chain controlled by just a handful of countries. But if these new batteries end up mostly built inside one single country anyway, the world has not truly solved that original problem. It has simply moved the same problem over to a new material. Still, something genuinely important has changed here, and it is hard to ignore. For the first time in 30 full years, lithium is no longer the only real option sitting on the table. An idea that started all the way back in 1966, got quietly abandoned for decades, and looked completely dead by almost every measure available, is now rolling off real factory lines and heading into real cars that real people will actually drive. That almost never happens in the history of technology. Most ideas that get left behind for 40 years or more tend to stay left behind forever, forgotten in old research papers nobody ever reads again. There's a bigger lesson worth sitting with before this story wraps up. The problems with lithium were never some hidden secret nobody knew about. The fire risk was documented for years by engineers who understood it clearly. The cold weather weakness was measurable from the very first lithium batteries ever built, decades ago. The supply chain risk was obvious to anyone who simply looked at a map of where lithium actually comes from. But when something works well enough, and the profits keep flowing in steadily, most industries stop looking hard for something better. It usually takes a real shock. A fire that costs $5 billion, a price that jumps 8 times in 2 years. A supply chain that suddenly feels far too fragile to depend on before anyone seriously turns to look at the alternative that has been sitting quietly in the background the entire time. Sodium sat in research papers and university labs for more than 20 years, waiting patiently for the world to need it badly enough to finally pay for it properly. That moment has arrived now, and the batteries rolling off assembly lines in China today are proof that it was worth the wait. If this kind of story is the kind of thing you want more of, make sure you hit like and subscribe, and turn on notifications so you do not miss the next one. We are going to keep digging into the quiet breakthroughs that end up changing everyday life before most people even notice they are happening. So here is a question worth leaving you with. Do you think sodium batteries will actually replace lithium in your own lifetime? Or does lithium still have enough strength left to hold onto its throne? Drop your answer in the comments below. And if you want to see how this same battery war is playing out in electric cars specifically, check out the related videos linked on screen right now.